Hello everyone, welcome to session 3 of module 3. So in this session we shall discuss on what do you mean by perceptron, the representation power of perceptron, the perceptron training rule. Let's begin now. So what do you mean by perceptron? Perceptron is a single layer neural network which is mainly based on a single unit. See, this Perceptron is a linear classifier, or it can also be called as a binary classifier. It is used in supervised learning. So, a perceptron takes a vector of real valued inputs, calculates a linear combination of these inputs, and then output the values. If the output is greater than 0, then it will result as 1. And if it is lesser than or threshold value, then it will result as -1. So you can see the formula in detail. Before getting into this, we shall see the major important parts of perceptron. So here the first part is with respect to the inputs. So the inputs are, you can see here, x1, x2 till xn, and next one is the weights and bias. Here you can also see this w1, w2 and wn. So these are called as weights which are associated with inputs along with the bias value. Here the bias values are x0 and w0. And the third important part is the net sum value. This is the value that what we receive as a net sum value. And the fourth one is our activation function. So let's see how does it works. See, the perceptron works on these simple steps that what I have explained. First one is all the inputs, that is x1, x2 till xn, are multiplied with their respective weights, which is called as w1, w2 till wn. So let's call this entire value as a simple value called as k, or add all these multiplied values and we call them as weighted sum. This entire term is called as weighted sum. So what I do, I assume that there are 5 inputs are there, x1, x2, x3, x4 and x5. Assume that there are 5 inputs are there. So what I do, I just multiply these inputs, that is x1, x2 till x5, with their respective weights. So here how do I write as your weighted sum? That can be written as summation of k is equals to 1 till 5 inputs, and this entire term is called as your net value. So this can also be, this is the total weighted sum value that what I have received from this equation. And after this, you apply the weighted sum to the correct activation function. So this entire value is sent to the activation function. Here, my activation function that what I have used in the perceptron is step function. So this activation function will tell you, in short, this activation function are used to map the input between the required values like -1 or +1, +1 or -1. So this is why we need our activation function. In a simple notation, so imagine that an additional constant here that I have already said that it is x0 and w0 are used. We always keep x0 as a constant. So that entire term can also be written as summation I is equals to 0, because we have used your bias value also, that is W0 and X0. For that I is equals to 0 till n, that entire term will be written as Wi and Xi, which is greater than 0. So in general, in the vector form, we can also write it as vector of weights multiplied with vector of inputs should be greater than 0. So this is how we write the notations with respect to the perceptrons. I hope you have understood. In general, I will tell you in short. So the output of this perceptron, either it has to return +1 or -1. When it returns +1, if the linear combinations of these inputs along with the weights, combination of all these things, if it is greater than our threshold value, then it returns 1. If it is less than our threshold value, then it returns -1. So I hope you have understood this one. Let's see the representation power of perceptrons. See, we can view the perceptron as representing a hyperplane decision surface in n-dimensional space of instances. This perceptron outputs +1 for the instances which are lying on above this side, and the instances which lie below this hyperplane surface, which outputs as -1. And the equation for this decision hyperplane is written as vector of weights multiplied with vector of instances is equals to 0. See, there are some of the instances, that is a positive and a negative instances, that cannot be separated by this or any hyperplane. The instances which can be separated are called as linearly separable set of examples. Here this decision surface represented by two input perceptrons, and here the first diagram you can see here, it represents a set of training examples and decision surface of a perceptron that classifies them correctly. And in the second picture you can see a set of training examples that is not linearly separable. In this decision surface you can see here it is a negative instance, here also negative instance, and here there are positive instances. Means these are the instances which cannot be separated linearly. And here x1 and x2 are your perceptron inputs, and positive examples are indicated as plus and negative as minus. See, a single perceptron can be used to represent many Boolean functions that can be used to represent some of the Boolean functions like AND function, OR function, NAND, and NOR functions. Let's consider an example here. So we assume the Boolean values as 1, that is positive 1 for true, and 0 for false. So let's solve this AND function, and also we'll try to represent by using the perceptrons. So in order to represent this Boolean function and Boolean function, we try to set some of the values here. So the value for W0 is set as 0.8, that is minus 0.8, and with respect to W1 and is equals to 0.5, and W2 is equals to 0.5. So why I have taken W1, W2, I will explain you in detail. See, there are two inputs are there. One is A, can also be used as x1, B as x2. So I represent first the Perceptron. So there are two inputs are there. One is with respect to A and another input is B. So here I take it as x1 and x2. So these two values, that is x1 and x2, are given to the next step, that is summation. So these two inputs values are summed up with the weights. The weights are with respect to x1 is w1, which is already denoted as 0.5, w2 as 0.5. Along with this we have a bias value. That bias value is taken as w0 is equals to minus 0.8 and x0 is taken as a constant as 1. So those entire value is computed as summation I is equals to 0 till n, that is wi into xi. So the output, whatever which is received from these combinations of values, is given to the activation function. The activation function that what we have used is a step function. So that step function will produce an output which lies either as a positive 1 or negative 1. So we'll try to compute these values by substituting the x1 and x2 in the formula. The formula we have already seen that the output is equals to, that is output from x1 to xn is equals to, it will give either positive 1 or negative 1. If it wants to receive positive 1, the condition is if w0 plus w1 x1 plus w2 x2 should be greater than threshold value. Here I have set it as a threshold value as a 0. It would return minus 1 otherwise. So by substituting these x1 and x2 values, we try to predict whether we have received the actual value or not. Let's consider the first instances. So the first one is if x1, that is a is equals to 0 and b equals to 0. If this is the condition, the expected output for this one is 0. Let's try to compute these values. So according to the formula, that is the output will be given as w0 plus w1 x1 plus w2 x2. Let's substitute these values. As we know that we have already set w0 as minus 0.8. So minus 0.8 plus w1 is 0.5 into 0 plus 0.5 into 0. So the value is minus 0.8, which is less than 0. We have already seen that if the output value is lesser than the threshold value, the output could be the minus 1, or it can also be taken as for our problem it will be taken as 0 or minus 1. Similarly, for second one, that is a is equals to 0 and b equals to 1. Substitute the values in the formula. So we get a 0.8 plus 0.5 into 0 plus 0.5 into 1. So the value that what receive is minus 0.3, again which is less than 0. The output will be 0 or minus 1. Similarly, for third one is a is equals to 1 and b equals to 0. So we do receive the same value, that is minus 0.3, which is less than 0. The output is either 0 or 1. But for fourth condition here, a is equals to 1 and b equals to 1, and when we compute the value is minus 0.8 in plus plus 0.5 into 1 plus 0.5 into 1. So we get the value as 0.2, which is greater than 0. When we receive the value which is greater than threshold value, the output will be plus 1. So as we already discussed, the output is for these are 0, 0, 0 and 1, and we have received the same thing. This is how we represent the perceptron for AND function. Let's see with respect to the OR function. See, as we have done with the AND function, similarly we try to compute the values with respect to the OR functions. So the representation of the perceptrons for OR function is represented like this. A and B are these are the two inputs, and which is represented as x1 and x2. Similarly, the weights are initialized and it is performed like this one, that is w1 is equals to 0.5, w2 is equals to 0.5, and here the bias value as x0 is equals to 1, and w0 here we have taken as a minus 0.3. In the previous AND function we have taken as a minus 0.8, but I have changed little bit so that in order to get the final value as we expected. So this summation value, again it is given to the step function, so it will decide whether you will receive the output as a positive or negative values. This is my output. So here similarly the summation is I equals to 0 till n wi is equal into xi. So this is how I represent my perceptrons for OR functions. So whether this representation is correct or not can be computed by substituting the values in this formula. The formula is already we have seen, that is output is equals to w0 plus w1 x1 plus w2 x2. So the output will be given as positive 1 if it is greater than my threshold value, otherwise less than or equal to, otherwise as minus 1. Here for my problem I have taken minus 1 as a 0 for easy understanding purpose. So let's substitute the values in the formula by taking the instances. First instance could be the x1 is equals to 0, and it can also be taken as a is equals to 0 and b is equals to 0. So the expected output is 0. Try to substitute these values in the equation that we have already seen. With the w0 we have already set it as minus 0.3. So minus 0.3 plus 0.5 into 0 plus 0.5 into 0. So the output will be minus 0.3. Again it is less than 0, the output will be 0 or minus 1. Similarly for second one, a is equals to 0 and b equals to 1. Substitute the values, that is minus 0.3 plus 0.5 into 0 plus 0.5 into 1. So you will get it as value as 0.2, which is greater than 0. So when you get a value greater than threshold value, the output will be 1. For the third instance, see, you can see the values as 0 and 1 here, as we expected as the values. Similarly for a is equals to 1 and b equals to 0, substitute the values as 0.5 into 1 plus 0.5 into 0. Again you will receive 0.2, which is greater than 0. The output will be 1. The output will be 1. And for the fourth instance, so we have received with the third one. The fourth instance is a equals to 1 and b equals to 1. So substitute the values minus 0.3 plus 0.5 into 1 plus 0.5 into 1. So the value is 0.7, which is greater than 0. So the output will be 1. This is how we represent the Boolean functions using the perceptrons. So you may ask the question, sir, why you have taken W0 is equals to minus 0.3 and W1 as 0.5 and W2 is also equals to 0.5. See, this is just to represent your Boolean function. I have taken the values directly, but in reality it is not the same thing. So these values, weights values are taken randomly initially. So if we do not get as we expected output, so we keep on updating the weights. So finally, if we get the output what we have expected, there we stop the weights values and try to use those weights to represent your Boolean functions. I hope this you have understood clearly. See, while representing the Boolean functions using perceptrons, I have taken the weights values directly. So I have not explained how to take actually the weights with respect to the perceptrons for an instances or for an inputs. So let's discuss how these weights are taken. So if we are interested in learning networks of many interconnected units, let's try to understand how to learn the weights for a single perceptrons. So the main goal is for perceptron training rule is we have to learn the problem where it is used to determine a weight vector that causes the perceptron to produce the correct value, that is either it may be the positive one or negative one as an output for the given training examples. See, there are several algorithms which are known to solve these learning problems. Here we considered two types of algorithms, that is, one is perceptron rule and delta rule. So these are the variants of LMS rule which we have already discussed in module 1 for learning evaluation functions. So these two algorithms will guarantee to converge somewhat acceptable hypothesis under some different conditions. See, these are important to artificial neural network because these will provide the basis for learning networks of many units. So one way to learn an acceptable weights vector is to begin with the random weights, then iteratively apply the perceptrons to each training examples, and modifying the perceptron weights whenever it misclassifies an examples or misclassifies an outputs. So this entire process is repeated, iterating through the training examples as many times as needed until the perceptrons classifies all training examples correctly. And the next one is these weights are modified at each steps according to the perceptron training rule. So which revises the weights Wi which are associated with an instance xi according to the rule. So let's see what is the rule is. And the rule is Wi is equals to Wi plus a delta Wi. Here the delta Wi is equals to n or eta t minus o multiplied with instance, that is xi. Here t is the target output for the current training example. O is the output generated by the perceptron, and n is a positive constant which is called as a learning rate. So the role of a learning rate is to moderate the degree to which weights are changed at each steps. So we usually keep as much as small values for this learning rate. Here sometimes we use as a 0.1 and is sometimes made to decay as the number of weights tuning iterations increases. So one of the major drawback for this perceptron rule is perceptron that will finds a successful weight vector when the training examples or instances are linearly separable. So it can fail to converge if the examples are not linearly separable. Why should this update rule converge towards successful weight values? So to understand in detail, we shall take some of the specific cases. So let's consider in this case if the t minus o is 0, so making delta wi as 0, so that no weights are updated, the weights remain same. Suppose the perceptron outputs the value -1 when the target value is +1. To make the perceptron output +1 instead of -1, in this case the weights must be altered, that is the weights are increased. For example, if xi is greater than 0, then increasing wi will bring the perceptron closer to correctly classifying the example. And on the other hand, if t is equals to -1 and o equals to 1, then weights which are associated with the instance x will be decreased rather than increasing. So let's consider an example how this weight update rule, that is a perceptron training rule, will works. So let's consider a simple problem here. Consider the following training set and identify the weight vector for 2 epochs, that is 2 iterations. So we have one instance, and that is x1, which has 4 features. The values are 1, 2, 0 and -1, and the desired output is -1. And here the n value is kept as low as possible, as we already said that it is 0.1, and this initial weight vector, that is w0, is taken randomly. So let's try to solve the problem, and we have some of the steps to solve that problem. Let's see that one. To solve that problem, there are 2 important steps are there. The first one is you have to identify or calculate the network output. So how do you calculate the network output here? This is a formula, that is a linear combinations of weight vector and instances. So if it is greater than threshold value, then it will return as a +1, otherwise it will return as -1. Remember, if we do not get as expected or desired output value, then the only option that we are left with is to update the weights. So again, how do we update the weights? That by using this weight update rule. So let's consider by taking the actual values. By taking these steps, we'll try to solve that problem. So let's begin with the problem by taking the first step. The first step is to compute the output. Here the output is equals to wi into xi. So here what is the wi is? Wi is, the first one is 1, -1, 0 and 0.5, which is multiplied with 1, -2, 0 and -1. So we receive the value as 1 plus 2 plus 0 minus 0.5. So here we get 2.5. So which is 2.5, the value that what we have received here. So this value is applied for the sine function. There is a sine of 2.5, that what we receive is +1. So but what we actually expected is -1. So hence the correction is needed in this step, because the expected value is -1, but what we have received is +1. So the step second is we have to update the weight rule, weight with respect to the instances. So how do we update? The update is wi is equals to wi plus delta wi. So we need to identify this delta wi. So for this formula we have n t minus o into xi. So substitute these values, as we know that the learning rate value is 0.1 and t is the value, target value, that what we need, minus the output what we have received, that is +1. So into that xi is nothing but your instances, that is 1, -2, 0 and -1. So here you will get as -0.2 into 1, -2, 0, -1. So finally we receive the delta w1 as -0.2, 0.4, 0 and 0.2. So therefore when we substitute these values in the formula here, for this formula, that is that updated rule, that is w2 is equals to w1 plus delta w1. So you substitute these values in this formula, so you will get w2 as newly updated as 0.8, -0.6, 0 and 0.7. So this is my updated weight. So this again the updated weight is given to the next iteration. Let's see that one. So you can see the equation, that is w2 into x2. Here w2 is updated value, that is updated weight value. Again it is multiplied with x2. x2 is same as x1. So if we substitute these values in the equation, we get the value as 1.3. So if I apply the sine function for this 1.3, again I receive +1. Here you can observe one thing, that in the previous iteration we have received 2.5 and also in the second iteration we have received as a 1.3. Even if we continue for the next few more iteration, we may receive the value lesser than what we have current value. So if we keep on updating like this, we may achieve the expected value. This is how we update the weight value by using your Perceptron training rule and also weight update rule. So this completes your session 3 of module 3. Let's see in the next session. Thank you so much.